Due to technical difficulties, I did not record part 2 and part 4 of example 2 on 6.4 for complex roots in polar form, the product, quotient, roots, etc. So here is part 2. We're finding the fourth roots of z equals negative 16. So let's change that to a complex number in rectangular form. That just means the real part would be negative 16, the imaginary part would be 0. So the modulus would be the square root of negative 16 squared plus 0 squared, which is just going to be 16. Then we're finding the fourth roots, so n would equal 4, and k would be 0, 1, 2, and 3. The angle is theta, and I found that just by graphing our point. The real point is the x value, the imaginary point would be the y value. So that would be the inverse tangent of 0 over 4, 0 over 16, negative 16, which would be the angle pi, because the tangent of 0 is pi. Or 0, but pi is where that point is located. Okay. So here is the polar form for the rectangular coordinate of the complex number z equals negative 16. So then we follow our formula for roots. We're doing the fourth root of 16, which is 2, times the cosine plus I sine of pi is the angle, but then we divide by n, which is 4, plus 2 pi k divided by n. So that would actually be a 1/2 or a pi halves k, right? Let's write that in. Oops. Plus pi halves k. All right, so fourth root of 16 is 2 times cosine plus I sine of pi fourths when k equals 0. Then 2 times cosine plus I sine of pi fourths plus pi halves when k equals 1, which is 3 pi fourths. And then 2 times cosine I sine of pi fourths plus 2 times pi over 2, which means we're adding pi. So that would be 2 cosine I sine of 5 pi fourths, which technically based on the range of the angle, we should do 2 times the cosine plus I sine of, instead of 5 pi fourths, it would be negative 3 pi fourths. So this way instead. And then we would have pi fourths plus 3 for k times 2 pi times pi halves, so 3 pi halves, which gives us 7 pi fourths, which we can change to an angle between negative pi and pi as negative pi fourths. So an interesting thing about roots is that they will be equally spaced around the origin if you were to graph them. So these complex roots of negative 16 would be equally spaced at pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. You know, it's 360 degrees all the way around. So divide by 4, and you've got 90 degrees. So each point is a 90-degree rotation from the previous point. That would be for fourth roots. Now, another interesting thing about being able to find the complex roots is back in secondary 3, if we said, let's find the fourth roots of a negative number, we would just say, oh, that's not possible. There are no fourth roots of a negative number, because there's nothing you can multiply together to get a negative, multiply together 4 times and get a negative number. Unless, of course, it's complex numbers. And so that just brings a whole new dimension to finding roots. So our fourth roots are 2 times the cosine I sine of pi fourths, 2 times the cosine plus I sine of 3 pi fourths, 2 times the cosine plus I sine of negative 3 pi fourths, and 2 times the cosine plus I sine of negative pi fourths. Okay, let's look at example 4, which is kind of similar to this one because instead of it being a negative number, it's just a positive number 1, which would put it at 0 degrees or 0 radians. Back in previous math class, if I told you to find the fifth root of 1, you would say the answer is 1, right? But now we're finding complex roots as well, so we have 5 roots total. and only the first of those 5 roots is 1. So what we would do is find the magnitude, which would be the square root of 1 squared plus 0 squared, so that's 1. And then find the angle, which if I graph it, it's obviously the inverse tangent of 0, which is 0, and that corresponds to our graph at an angle of 0. So we have 1 times the cosine plus I sine of 0, n is going to equal 5 because we're doing fifth roots. That means k will equal 0, 1, 2, 3, and 4. So then following our formula, we do the fifth root of 1, which is 1, times the cosine plus I sine of 0 divided by 5, plus 2 pi divided by 5 times k. So our first root is 1 times cosine plus I sine of 0, and of course that just equals 1, so the fifth root of 1 is 1. And then the first complex root is 1 times the cosine plus I sine of 2 pi fifths. That would be if k equals 1. So we're adding that to 0. Then the next one would be 1 times the cosine plus I sine of 4 pi fifths, because we're taking 0 plus 2 pi fifths times 2. And then the third one would be the 1 times the cosine plus I sine of 6 pi fifths, because it would be 0 plus 3 times 2 pi fifths. And we can change that to an angle between negative pi and pi if we would like to. I'm getting a little lazy with that, but I don't think it's a big deal unless they actually ask you to put the answer in that range. And then our last one would be 0 plus 2 pi over fifths times 4, so 8 pi over fifths, which would be negative 2 pi fifths if we do the range from negative pi to pi.